Hello Math 30-2 and welcome back. Today we are looking at exponential functions or the equations and graphs of exponential and logarithmic functions and applying them to real life situations. So we're going to look at their graphs and apply them to real life situations and see how this could help us out. Our first example here, I'll show you what I mean through the examples in the book here. So here it says, in 2012, the population of a country was, or the education, university population of the country was 160,000. And was increasing at an annual rate, so every year, by 4.5%. The growth in the university population can be represented by the exponential function of this here. Well, that makes sense. This is my initial population, and we're always increasing. We have 100%, and it increases that 100% by 1.0 or by 4.5%. So that's how we get that 1.045. You'll learn about more how to make these equations later on in the next chapter. Okay, so now where P represents the university population of the country as a function of the number of years N. Perfect sense, okay? So, N is the number of years, P is my population, okay? So, the function representing is disguised as this function. So it's like in a little disguise is really that function. Well, what is the A and B value of that function? Well, this initial population, A, is equal to 160,000. That is my A value. Why? Because that's kind of my y-intercept, isn't it? That's my initial population. That's my y-intercept. That's the A value. Now let's take a look at the next one, this B value. What are we increasing by? We're always increasing. What's the power? The base to the exponent is the 1.045. Okay? And looking at this, knowing it is greater than 1, that means it's an exponential function and it's an increase. From quadrant 2 to quadrant 1, it increases. Look at that. And because A is positive, it goes from quadrant 2 to quadrant 1, increasing. Good. Good to know. Okay? That automatically we know our graph is going to look like this. And we know the intercept and everything. Now, use the graphing calculator to graph the following, and let's make our window. But we want to look between those 2 years. So first of all, how many years is this? From 2012 to 2040 is 28 years. Well, I want my graphing calculator to go a bit beyond, so I'm going to say 30 years. All right? So I want 30 years for this. So first, I'm going to put this in my graphing calculator. So here's my formula. It's already punched in right there. If you notice how I put it, I said y is equal to all of this to the power of x. Okay? So 160,000, 1.05 to the power of x. Then I did my window. Here's how I did my window. I have my x min is 0 because at 0 years is 2012. That is when we start. Notice I didn't put 2012 for my x min. No, I put 0 because that is year 0. Okay? Then I said my max years, I said 30. I went a little bit beyond here. That's going to be 2042. That's okay, I just went a little bit beyond. And maybe I should count by here instead of ones, maybe by threes. Okay? So I'm counting by threes. That's my scale. Next, let's take a look at my y min. I said some people would have wanted a 0 as y min, which is fine. There's many different answers. I put mine at 150,000, which is a bit less than our y-intercept because we're only looking there and we know it's increasing, so it's not going to go lower than 160,000, but I still want to have some wiggle room. And then I said my max is 400,000. Now, let's take a look. Maybe I put 250,000, okay? And let's look at what my graph looks like. If I look at this, I go, oh, wow, I don't see nearly enough this way. My x is too big compared to my y. So then I'd have to increase my y, maybe 400,000. And I look at that, oh, this looks better. Ah, that's good. It takes at least 3/4 or 2/3 of it, so I'm going to keep it at that. I could even put to 500,000 if I want to really get a nice view of everything. But 400,000 is good enough. So my window is, for my x value, my window is, we have, my min was 0, my max is 30, and I counted by 3s. You might have counted by 5, 6s, something like that. So I have 10 ticks along. Oh, my y scale, I should change my y scale, maybe counting by 10,000. There. So I at least have a little bit of scale that I could see. Maybe even 15,000 would be better too. Change that to 15. There we go. So it's a little bit better, so I could see some ticks there. Now, let's take a look at this. My y, I started at 150,000. You might want to start a bit less than that. Okay? It's just, then we have my max. I said it's 400,000. You might want to go a bit more. And I counted by 15,000. Okay? So that's everything. Oh, I have 150,000, so 15,000. I'll just erase that, correct it. Okay, now, let's take a look at this. Now it says, using the features in our calculator, determine the population in year 2015. Well, in the year 2015, that's 3 years from 2012. So that is when x is equal to 12. So I'm just going to hit trace, and find 3. That's 3 years. Oh, when x is equal to 3, not 12. What am I thinking here? Getting ahead of myself. 3. So we get 3, and let's plug in the value there that's shown. I have then my y value, my population will be 182,567. 587. Okay? And that is my population. I rounded up because 0.58 of a person, that's not a person, so just round up for that one. Okay, next one says the number of years for the population to double. Now I look at that. What is the double population of 160,000? That's 320,000. Now we want our equation to equal that 160,000 multiplied by 1.045 to the x, or to this case n. We want to know when it's equal to that. So what I'm going to do is put in y2, because that's my other equation. We're making the two equations equal. In y2, we're going to put in 32000, and we're going to graph it. Ah, there we go. Now, when these two equations are equal, it's at that intersect, right? In this equation, we want to know the x value when it's that value. So I can push this here, and I want to find my intersect, and get close. It's around there. Push enter 3 times, and I end up getting 15.7. So it's 16 years. And that is my y value. Remember, every time we find our y value, we have to do the other equation. Here is example number 2. It says, the number of fish in a lake is decreasing by 5% each year. Interesting. So, each year as a result of overfishing. The number of fishing, t years, is given by the formula like this. Now, if we look, it's 0.45. That means my graph, we already know, is most likely looking like this here. Right? It looks like that. It's a decrease from 2 to 1. Now, we don't know if my initial is negative or positive. I'm assuming it's positive because this is my initial population. So I am probably a positive, but I don't never seen a lake with negative fish. Oh well, anyway. So what type of function is being represented by the formula? Well, this is exponential. Exponential decay. And this is a decay. It is not a growth. Why? Because it is between 0 and 1. My b is in between 0, there shouldn't be an equal sign there, and 1. Therefore, it is an exponential decay. Now, there are 2,500 fish present in June 2012, which is our year 0, we'll say. Write the equation of the function, which can be used to enter into the calculator. Okay, so y is equal, which is this. Y is equal to my initial population is 2,500. And we have 0.95 to the power of x. That's what we could put into our calculator. Now it says, explain how to use a calculator to determine how many fish you'd expect to be present in June 2017. Well, in June 2017, that is 5 years from now. So that's 5 years from 2012. So what I'd have to do then is I'm just going to trace the value at 5 years. And that's all I have to do. I'm just going to trace the value in 5 years. So I'm just going to do that right here quickly. Clear. Clear. And put in my calculator. We have 2500, 2,500. And we have 0.95. Bracket to the power of x, and I'm going to window. First of all, I have to change it. My y-intercept is now 2,500. So 0, 0 to 30, we could keep that in 30 years from now. And now my y min, I'm going to say is going to be, my y min is going to be 0. My y max is going to be, well, 2,500, so I'm going to say 3,000. Because 2,500 is my intercept, and it's going down. And my scale, I'm going to count by 50s. Here's my graph. Let's see. It should work. Oh, I have 300. It should be 3,000. I'm going to count by 500. There we go. There's my graph. See, even I made the odd mistake. And there's my graph. Oh, look how nice that looks. Perfect. So I'm just going to trace and find it. That's 5 years from now, so we trace. Oops. Trace, and I want 5, enter, and that's how I get my value. Okay, so my value is 1,934. So trace, and we get 1,934. Okay, that's how we do that one. Next one says, how many years to the nearest tenth would it take for the fish population to reduce to half the number of 2012? Well, this one, we have to do the same thing. All we're going to do for this one is we have to make it equal. So we want half the number. It's half of 2,500. That's 1,250. And that is going to be equal to 2,500 multiplied by 0.95 to the x. Okay? And so we have our y2 and y1. We want to know when these two are equal. So I just put in here 1,250. I graph it, and then I find my intercept. And it's around there. And I get 13.5, so in 14 years. Okay? Because this is showing where the two equations are equal. Okay, next one here. Second last one before we're done. It says, in chemistry, the pH of a solution is used by that equation, where H is the hydrogen ion concentration. Okay, so in moles per liters. On the grid, sketch the graph of the pH axis. So we know, first of all, this is -1. So A is equal to -1. All right, and my B is equal to 10. My base is 10. So if I look, my base is 10, so my initial graph should look like that. But now because it's a negative, it's going to flip it. So my actual graph is going to look like this. Okay? So that's what my graph is going to look at. Huh, good. Okay? Oops, sorry. So it's going to look something like that. But now it tells us it wants a window like this. So there's my y value, my x value. So let's take a look at my window. I already typed in my equation, and we want our windows that small. So x is 10 second e to the -6. Okay? Oops. Now the next one is 10 -5. Now the reason why this is because we're talking about very small concentrations. And then it wants to be counted by ones, and then here it is going to be 3, 7, and 1. So I graph it, and my graph looks like that. Just a little bit. So y min 3, 7, and 1. I believe that's what it says. Yep. So that's what my graph looks like. Now, if I had my window as before, it would look kind of what we drew there. But because we want the window in this way, because we look at something so small, the window, it's zoomed in into a little tiny spot. Okay? So now it says, determine the pH of the solution to the nearest tenth of the hydrogen atom concentrated at that thing. So this is the concentration, where H is the hydrogen concentration. So this is my x value. So to find this, I'm just going to trace. This is my x, because H is x. So I hit trace, and I want 3.4 and -10, or -4. And I graph it. Oops. I don't know what I did. Trace 3.4 to -4. Push enter. Whoop. trace. Sorry, I just had to change my window. I accidentally punched in one of my dimensions wrong. That's why it wasn't working. So I have to look at this. I go 3.2, or sorry, 3.4. So I want to go my graph, trace, and we go 3.4. And second into the negative, what was it, 4. And we push enter. And I'm going to get 3.46, which is the same as 3.5. So the term is solution to nearest hydrogen molecule. pH, the pH is 3.5. I'm just going to round up because 3.46 is the same as 3.5. Next it says, a patient gave a urine sample which was found at a pH of 5.7. What was the hydrogen concentration? So this is now my y value. So I have to put that in. 5.7 is equal to negative log x. So we want the second value to be 5.7. So we have to trace and find the intercept. So we have 5.7 and we're going to graph it. Oh, my tracing is way up there, so I'm going to change my window again, and my x min, I'm going to put at 0, or 0, and I'm going to graph it. There we go. 5.7. So if I look here, it looks like it doesn't touch, but remember, my asymptote is the y-axis, so it goes infinitely close and all the way up to there. So I'm going to just change my window here and put my thing at 0.001 and see what it looks like now, just to make my thing a little bit smaller. And there I can see my intercept, so I'm going to make it a little bit more. So 0.00001 and graph it, see what this one looks like. And there we go, I found my intercept. So I'm going to now calculate, and I want my intercept. So I'm going to go all the way over. So if you remember, the reason why I changed my window is because I couldn't really see the intersect, but I knew the asymptote, so I had to compress it and narrow it in on my x values. So my first curve's around there, and I get 1.996 times 10 to the negative 6. So we get around 1.995 times 10 to the negative 5 is my concentration at that point. Okay? And that's how we do that one. Hopefully you get that. So here we go. Last question. It says, carbon dating. Now carbon dating, normally when we talk about this, we're using half-life. So my B value is going to be half. It's decreasing. So this one's a gain is going to be an exponential decrease from 2 to 1. Okay? So it says, state the suitable domain and range for the exponential function. So we're looking at carbon decay, radioactive, of the Earth past, living organisms, carbon remains of the body. However, when the organism dies, new carbon ingestion portions of carbon-14 create. So here we go, estimate 80 years of age, so on and so forth. Here's my formula. So what is the suitable domain and range for the function? Okay. Well, for this one here, my domain is, well, x must be just greater than year 0, right? X has to be greater than or equal to 0. That's it. And x is an element of all real numbers. Because from the year that the thing was put into play, like the animal died or whatever, that's when you start. The next part says, what is my domain and what is the suitable range? Well, So years of organic, well, my suitable range could be anything right now. So right now, let's try 0, or percentage of carbon. Well, it could be anything. Well, how much percentage will we have left? So P is my percentage of carbon. I can go from 0 all the way to 100 is my carbon, right? So we can only have between 0 and 100%. So that is my range. Okay, now next one says, graph the function using a graphing calculator. Okay, with those windows. So let's graph this function. So I have to put this in, and it gives us the window and everything. So we have 100, because we start off with 100%, and it's a half-life, 0.5, and we go down 0.5 every how many? Well, x over 3,500. So that's bracket x divided by 37530. So the half-life is every amount of those years. And I made a mistake punching that in. It's 55730. Oh, it's late in the day, making a lot of mistakes here. So I graph it, but I have to change my window. Here's my window. It tells me my window is 0, 2,000, 20,000. And we want 10,000. And here we want to have 0, okay, 100, and then 50. Let's go with 50. So there is my beautiful graph. Oh, and I have to delete that one part. That's 5.7. Delete, graph. Okay? So now it says, graph the function using that window. So we've done that. Now it says, on May 1st, 2012, a family in Whitehorse was digging up their basement, and this article's on here, and they thought the bones were to be about 10,000 years old. But the carbon dating results required verification. So they needed carbon dating to require verification. So the skeleton of the bison is about 10,000 years old. What percentage to nearest 100 of carbon-14 should be found in the bones? So we put in 10,000. Well, no, 10,000. And we're going to graph. Oh, sorry. So we want 10,000 years old. So that's my x value is 10,000. So this here is my x value, right? 10,000 years old. So time is always your x normally. So I'm going to go trace, and I want 10,000. I hit enter. So there should be only 28 or 29.8, which is 30% left. Next one says, a bone fragment with the carved image of a mammoth was discovered. The carved image of the mammoth was discovered in southern United States, Florida, in 2011. The carbon dating test indicated that approximately 20.3% of the carbon-14 was left. So they had only 20.3% of the carbon-14. The estimated age of the bone fragment to the nearest 1,000 years. So now this one, we have to do different. Our percentage left is 20.3. So we go like that, because that's my y value. And I'm going to find my intercept. And I keep on going, find my intersect, and I end up getting around 100, right there, 13,200 years, or 13,000 years. So it's around 13,000 years old. And that's it. Okay? Hopefully you understood this. If you have any questions, ask tomorrow as we work on the assignment together.